for today, we're going to look at a state space model. So this is a new topic, and this is a big shift from what we've seen before, in the sense that we're looking at Laplace transforms, we're looking at frequency domain, and now we are going to go back to the time domain. And instead of based our analysis on Laplace transform, we are going to use linear algebra instead. The objective is the same, is to provide a model for a system and then use that model to simulate this particular system, but are now done in the time domain. And you may be asking, why do we need this new model now? Well, this by using linear algebra, we can make the simulation faster, and the first advantage of this. And the second advantage is that in our simulation, we can now choose which variables we are going to highlight. If you remember from assignment 2, the very last question, assignment 2, was a big block diagram, and I asked you to identify where speed, position, and acceleration were in that simulation diagram. And it's very hard to do. We can't simply pick points before and after integrators. That information is somewhere in the block diagram, but it's not explicit. It's not really something you can just pick at one point and probe there and get that information. For example, if the output was position, the integration, the signal just before the first integration is not necessarily the speed, because there is more going on. There is more sum blocks and stuff going on there. So to get now this, in these simulation models, a more explicit view of these variables of interest, we can use the state space models. And again, instead of using Laplace transform, now our analysis is based on linear algebra. And MATLAB is a very good tool to analyze these equations, because MATLAB is meant to be used with matrices. So that's the idea behind state space models, is to create a way to simulate high-order differential equations using matrices, and then implement this in a software such as MATLAB to solve for these matrices, these equations, more easily compared to Laplace. Another advantage here is that we are going to lower the degree of all differential equations. If you have a system that is governed by a fourth-order differential equation, here what we're going to do is to create 4 first-order equations and use that instead, which makes solving them easier. All right, so for a system with a differential equation of order n, we are going to end up with n first-order differential equations that will represent the same behavior. When you go into, some of you may be interested in control systems, and if you go into control system, most of the control system theory, modern control systems, use a state space representation rather than the classical control system, which is based on Laplace. So most of the theory there is based on what we covered here. And some of you will have more advanced control systems later. This will come in handy. So by the end of today's lecture, the objective is to represent differential equations using matrices, obtain the state variable model for a given system, and understand the role of state variables in the design process. So my picture here, for some reason, is not showing, but in your copy, it is. So this is, for those that are here, is supposed to be the space station. And one application of what we're going to see here is, for example, if you want to predict the future behavior, the future position of the space station given a control action, for example, an acceleration in a particular direction or a force applied in a particular direction, what do we need to know? What are the minimum set of variables that we need to describe the future behavior of the system given a current action to it? Here is another example. This is for surgical robot arms. This picture, again, for some reason is not showing here, but it shows better in your copy if you have a PDF or you're working at home. If you have a surgical robot arm such as this one operating on a patient, and you want to go from point A to point B, what parameters do we need to know in order to apply a force that will make this system go from point A to point B? Or we can also ask which parameters will influence the transient and the steady state value of that motion. By transient, I mean the portion where the system is moving, and the steady state value is once the system settles, where does it settle? So there are two sets of parameters here. One that will influence how it moves, and there's another set of parameters that influences where it ends up. Which one are they? How can we look at the equations and explicitly highlight the dynamics and the static part of this system, where we can use a state space representation as well. And if you're interested in this sort of research on medical robotics or projects, maybe for a fourth year project, come and talk to me. We can certainly find you some interesting topics to work on there. Okay, so let's dive into it. So what are state space? Well, to define what a state space is, we need to first define what a state is. And the state is the minimum set of variables required to predict the future state of a system for a given input. So we have the inputs given to the system. We need all its states in order to predict its future state. Let's put it this way. If I'm on a car and I want to know my position in 5 seconds from now, what do I need to know? I need to know, of course, my current speed, my current position. I need to know where I am. What else? What else I need to know? I need to know how fast I'm moving, right? The initial speed, and what else? Perhaps the throttle angle I'm planning on applying for those 5 seconds. So I need three pieces of information to predict my future state. The current state of the system, that is its position and its speed. And I need to know what action I'm applying to the system, which in this case would be the throttle angle. That's the input to the system. What about acceleration? Do we need acceleration? Well, acceleration comes from the throttle, comes from the input, right? So it's given through that applied force to the system. So we don't need it as a state. We need it as an input. So we take this set of variables and we define them as the state of the system that will allow us to predict the future state given an input. And you are going to arrange these in a vector. This vector x, they're going to use that to notate all the states of the system. And this vector should here be transposed. I just didn't transpose it to save some space. So the t here means a transpose vector. So it's a column vector. And in our example, or the car, our states would have been the position and velocity. But if you go, for example, we have a complex electrical system, what do we need to know there? Well, we need to know all initial conditions in the system. We need to know if there are any voltages in capacitors, if there are currents in inductors, and so on. In addition, of course, to the inputs to that system, which could be a current, a voltage, and so on. So let's look at this example here. So let's consider this system as a mass spring damper system. U is the input, that's the force, and Y is the output. What variables do we need to know to predict the new state of the system when a force, a U of t, is applied? Now we are interested in the future position of this mass spring damper system. So to do that, we need to know first its actual position. And we also need to know its speed, how fast it is moving and when that force is being applied. So this vector here will transpose it. So we can define now 2 variables here. One is the speed, one is the position. How do I know that those are my variables? Remember that we want to define the system with the minimum number of variables that are required to predict its future state. Where do we find these variables? How do we go about defining them? Well, a good first approximation is to think about elements that can store energy. Anything that can store energy is a good candidate to be a state variable. What can store energy here? Well, first we have the spring. And the spring stores energy in the form of kinetic potential energy, kx squared. So it depends on the position of the mass. All right. What else can store energy here? Well, we have the mass itself, but it can store energy in the form of kinetic energy. And that kinetic energy is 1/2 of m y dot squared, x dot squared. I think I called it y, so let me just call this y and y dot squared. So I have 2 elements that can store energy. One depends on position, one depends on the speed. Therefore, those are good choices for our state variables. And that makes sense. For this particular system, once again, if you want to know where the mass is going to be in 5 seconds following the application of a force, we need to know its current position. We need to know its current speed. Do we need the acceleration? No, because the acceleration is got through, is given through the applied force. So 2 variables for this system, and this again would make sense because if you write a differential equation for this, we would have a second order differential equation, mx double dot plus bx plus kx equals to u. It's a second order differential equation, and you're going to replace that second order differential equation with 2 first order differential equations. So we need 2 independent variables. All right, so everything so far makes sense. So let's define our first variable here as y of t. That is the position of the mass. Let's call that x1, and x1 is the first element in the vector x. And then the second one is simply the position, which is y dot of t. That's the speed of the mass. And how can we now relate x1 and x2? So if x2 is y dot and x1 is y, x2 is the same as x1 dot of t. x1 dot of t. Okay, we'll come back to this equation later. All right, so once again, if x2 is y dot, x2 is equal to x1 dot. If you take x1 dot here, just take the derivative of both sides, we get x2. So that's our first step, is to define the state variables, the minimum set of variables required to describe the future behavior of the system. And now let's rewrite the equations we are used to, but instead of using Laplace, let's use these new variables. So for this particular system, if you do the sum of forces equals to mx y double dot, we get the equation that you see here. This is simply Newton's law. At this time, at this point, this is trivial. And we have 2 variables, state variables that we define as being the position x1 and the speed x2. So now let's rewrite this equation using our state variables. So remember that the objective is to convert these high order differential equations into first order differential equations. So when you now rewrite in equations, always use the lowest available derivative. The lowest available derivative. You understand what I mean? When we do this example, but let's look at the first element here. The first element is m y double dot, and where do we get y double dot? So x2, let me just write here, is y dot. So if you want to write y double dot as a function of our state variables, which options do we have? We could write mx1 double dot. Yeah, mx1 double dot. Or what else can we write? Yeah, exactly. Or x2 dot. These are the same. Which one we go for? Well, we don't want, if we convert this into a second order differential equation, we are just walking in circles. We didn't do anything. So instead of using the second order, we use the first order. Use always the lowest available derivative, which in this particular case would be x2 dot. So this equation can now be rewritten using the variables we created, and this becomes m y dot is x2 dot plus b times y dot. What do we do with y dot? So do we go with x1 dot? Or do we go with x2? We go x2, always the lowest derivative, which in this case is x2. And then plus k times y, y is x1. And this is equal to U of t, that's the input force. Okay. So here we have our equation, now written as a first order differential equation. But I mentioned in the beginning that if you have a second order differential equation, we should end up with two first order differential equation. Here's one. Where's the second one? Well, the second one we can take from the definition of the variables here. This is y dot, which is the same as x1 dot. So here we have one equation, and our other equation is x1 dot equals to x2. So two equations for a second order differential equation makes sense. And you notice something interesting in these equations here. We only have one derivative, and each derivative that appears there is the derivative of one state, and that's exactly what we are looking for. If you want to know the future behavior of these states, find the equations that give them rate of change. That is x1 dot and x2 dot, and that's what we are highlighting in these equations. So our objective from now on is to convert this system into more equations, but in each of these equations, we'll only see one derivative. And that derivative will be explicitly of a state. And there's only one derivative per equation. If not, then we haven't finished yet. We have to rearrange it until we get it to this format. Any questions so far? Are we okay with rewriting this equation with the state variables? Is there anything needs further clarification before we move on? No? All right. No questions? Yeah. How I define them? Yeah, so to define them, so you're back here. If you want to know the future behavior of this system, we need to look at the current position and the current speed. So how do I know that that's what I need? Well, in this case, it's obvious. But if a system is more complex and you don't know where to place these variables, we can look at elements that store energy. In this particular case, we have two elements that can store energy. The spring that can store energy in the form of potential energy, and that depends on the displacement. So that's one of our state variables. And the other element that can store energy is the mass itself in the form of kinetic energy. And that would depend on the speed of the mass. So that's our second variable. Now, so I define them as speed, position, speed. I could have done it the other way. It doesn't really matter. So to that question, let's look at another example and see if we can figure it out there. Let's look at this one here. This is a electrical circuit, and we want to now define the state variables for this system. What do we do? Which are, if you want, again, our objective is to understand the future behavior of the system. What do we need to know about our system? Well, we first need to know the input. That's U. It's the input to it. What else we need to know? The voltage in the capacitor, very good. How do we know that? Because the capacitor can store energy in the form of electrical energy. And that energy depends on the voltage. What else? Along the same lines, we have another thing that can store energy here, the inductor. And the inductor stores energy that is a function of the magnetic energy, and that depends on the current. All right, so to know the future behavior of this system, we'll need to know two things: the voltage across this capacitor and the current through the inductor. Let me just check how I call these so I don't mess up my notation. Okay. Okay, so our first variable here can simply be VC, that is the voltage across the capacitor, and the second state variable can be the current in the inductor. And that's enough. That those are the two elements that can store energy. Those are the two state variables. What do we do next? Well, now we can start modeling this. And if you model this system traditionally, as we've been doing, we'll find a second order differential equation. So ideally, we'll end up here with two differential equations. Okay, so here is the system. And let's model it. So we define our two variables. X1 is VC and X2 is IL. So to start modeling, what can we do? We can start with this node. Let's call this node A. And in node A, we're going to do sum of currents equal to 0. And if you do that, what is entering that node? We have I of t, the current from the source, or U of t. That's called U of t. And that is equal to the current through the inductor, IL, plus the current through the capacitor. That's one of our first equations. And the second equation we can do is this loop equation here to find, just use Kirchhoff's law and find the sum of voltages there. If we call this, let's do the signs here. So this is positive, negative, positive, negative, positive, negative. We can do the sum of all voltages here. We have the current through the inductor as L DIL dt plus the resistor minus VC equals to 0. Why minus VC? Because look, when I go through VC to the capacitor, I go from minus to plus. And minus to plus. And everybody else goes from plus to minus. And that's the second equation. So in this equation here, we did sum of voltages equals to 0. And these two equations are sufficient to derive the characteristics of our system. We can go back to the first equation we wrote and replace IL with something else, because now look at this equation. We have three elements there. The first one is the input. We need that. The second one is IL. That's a state, so that's good. We can leave it as it is. The third element is IC, and IC is not a state, so we have to get rid of it. We can only write our equations as functions of states. IC is not one of them. If you look at the other equation on top there, we have IL, DIL, dt. That's a state, that's good. Then we have IL, that's a state, that's good. And VC is also a state, so we are good there. But the other equation, you have IC. IC is not a state. We have to replace that with a state. How do we do that? Any ideas? How do they go from IC, the current through the capacitor, to a state? Is there any equation relating them? What is a state? Well, VC is a state. The voltage across the capacitor is a state. So we could relate IC and VC by simply writing VC as dVC, IC as dVC dt. Now we replaced IC that was not a state with a state VC, its derivative. Okay. And now we are pretty much done with our equation. So here is one of them. Here is another one. And notice that these equations, once again, are now functions only of states and their derivatives. Right? Everything else, and the input, of course, because the input is required. So if you rearrange the first equation, we have it here, and then the second equation. Now let's rewrite these as a function of our states. What is dVC dt as a function of our states? C times dVC dt becomes, as a function of one of our states, is either x1 or x2. So it has to be x1 dot. Very good. X1 dot. That's equal to U of t. that's the input, that doesn't change, minus IL, which is another state, and it is precisely x2. The second equation there is I dl dt. Now you get it. The dil dt is x2 dot. So this is L x2 dot of t equals to negative R times IL, that is x2, plus VC, which is x1 of t. Aha, interesting. So these equations, look at the format of these equations again. These equations are only function of the states, and each equation has the derivative of one and only one state. And that's exactly the format we've been looking for. Two first-order differential equations to give the behavior of a second-order differential equation. Each of these differential equations is first order, and the derivative appears on each of the states. So our job is pretty much done. We know the derivative of each state. And if you know the derivative, we know the rate of change, we can predict where they go. The last equation that I have here is a new equation that I've introduced as the output equation. And in this particular example, the output equation is chosen to be the voltage across the resistor. It could have been anything else, but here is the voltage across the resistor. We can write that as a function of a state as well, V0 of t, and that's simply R times the current through the resistor, which is x2. Right, so three equations here. These two are the states, and that equation is the output equation. That's what you want to monitor in this particular system. But as I said, it could have been anything. It could have been the voltage across the capacitor. In that case, V0 would simply be x1. Right, but we're evaluating something else here. Okay, so these are the equations we just derived. I just divided both sides by L. So we now can explicitly see the rate of change of each state. And now we want to write these equations in a matrix form. And this matrix form will always take this format highlighted here. X dot equals to AX plus BU. So what do we see there? X dot is the derivative of our states. Remember that X is defined as X1, X2. We want that times is to be equal to a matrix times the states. So that's the state matrix we'll call, plus B times U plus another matrix times the input. So two elements, the state matrix and the input matrix. And we are again writing these equations as a function of the derivative of the states. Let's see how we can write this. So this is a we have two variables. We have two states, three states, and we have two equations. So this matrix A is a 2 by 2. Matrix B is a vector, is 1 by 2. What goes in each of these equations? Well, in each of these cells. Let's look at x1 dot. X1 dot is given by the top equation there. And we are now trying to recreate this equation in a matrix form. So we know that at this cell, we have to multiply that cell, and this cell, we have to multiply that cell. And then we add everything up. So what goes in those positions? Well, the coefficients of x1 and x2. X1 dot does not depend on x1, so that's 0. And it does depend on x2. The coefficient is -1 over c. And it also depends on the input u of t. So here we have 1 over c. Now notice that if you multiply out this matrix, this multiplies that, and then u over c multiplies 1 over c multiplies u, and then we add everything up. We go back to equation 1. With that in mind, you can look at the equation for x2 dot. And the equation for x2 dot is given there. It depends on x1, that is 1 over L times x1. It depends on x2, is, well, the coefficient is R over L, and there is no U in the equation, so we can just set that to 0. A lot of information here. Let's slow down a bit. What did we do? We simply rewrote the equations as a function, as a matrix format. If we want to multiply this out, we can have this times that, plus this is one of the equations. And if you do the second row, we have, can you see the yellow one? Yeah, this times that, plus this times this, plus that. So 2 equations, the yellow and the blue. And if when you multiply this out, we go back to the equation we started from. Okay, and that's the way you're going to define this state variables from now on. Any questions? No? Okay, so we did half of the job here. We created these equations for the states, relating the states and the input. Now we need a second equation, a second set of equations that will give us the output. So far we haven't even defined what it is, but we haven't written it formally. We have, again, the first equation is input and the states. Second equation, now we'll go from states to the output. And to do that, we will write this new equation here. Y of t equals to c times x plus d times u. So x is the vector of states, c is a matrix, d is another matrix that we had to find, and the u is the input. We defined our output as the voltage across this resistor, which turns out to be IL times R, or X2 times R. That's the equation, the only equation you need to represent to the matrix formulation. And to do that, we can rewrite, remember that x here is x1, x2. And the output only depends on x2. There's no x1, so that's where the 0 comes from. And x2 is multiplied by r. That's where the r is coming from. So that's the definition of the second one. And it does not depend on the input. So you can simply write plus 0 u of t. And that's it. Now we have everything we need. We have the 2 equations. The first one, x dot equals to ax plus bu, relates the input and the states. The second equation relates the output and the states and the input as well. All right, so the first equation was the first slide, the last slide, and then the output here equation, which is typically shorter, is simply a way to recreate y of t equals to x2 times r. Okay. Any questions? Yeah. Where we got y of t equals to x2r. Yeah, yeah. So this is the output of the system that we chose to be the voltage across the capacity, the resistor. All right. So the voltage across the resistor is simply R times IL. Yes, that's the output. Yeah. All right, but we could have chosen anything else. Could have chosen the current itself. Could have chosen the voltage across the capacitor. All right, that works too. Even the current, just have to reorganize the equation. Okay. Any more questions? All right, so let's now define the state space. That's the standard form. And these are the equations we are looking for. The derivative of the states as a function of the states themselves. In these two equations, one for the states and their derivatives, the second one for the outputs of the system that we define. So here are the steps for analysis. You can use this every time. Derive the differential equations of the system, define the state variables. Remember, look for elements that can store energy, and define define the state variables that way. Then rewrite the equations using the identified state variables. And the fourth step is arrange the equations in the as a function of the derivative of the states. So in each equation, we only want the derivative of one state, and we solve for the derivative of all states. Right? So if when you solve for the derivative of all states, we are basically solving for y dot x dot here. And once that is done, they can simply convert these resulting matrices, these resulting equations into matrices in the format we want. Okay, so let's do another exercise following these steps and see if that will make more sense. Let me look at my notes here so I don't mess up my notation. Let's do this example. I'll do a few examples today, times it. Okay. So here we have a mass spring damper system. We have two masses. Position of each mass here is denoted Q and P. And the U of T is a force. We are choosing the output of our system to be the position of mass 1. Or if we are still looking at a Laplace, we would say find the transfer function between P and U. It's the same statement. We are defining the output that way. So two positions, one force input U of T. And the question is, now let's write this in the form of a state space representation. What do we do first? Step 1, define the state variables. How many state variables do we need first of all? If you write, this is not as obvious, but if you write the equations of motion here, we'll find a fourth order differential equation, if you remember from the assignments. We'll likely need 4 state variables. What can they be? Let's focus on the position of mass m1. If I want to know the future position of mass m1, what do I need to know? I need to know its current position. I need to know its current speed. Its current position in its current speed. But I also need to know the same for mass 2. Its current position and current speed. So 4 state variables. Another way to look at this is what can you store energy here? What can you store energy? The springs. Yeah, the springs, both springs. What else? The damper dissipates energy, cannot store. Right, the masses. Right, the masses. So we have 2 springs. This spring stores energy, and the energy depends on Q. This spring stores energy, and the energy depends on both Q and P. We have 2 masses. This mass can store energy in the form of kinetic energy. That depends on Q dot, and mass 1 does the same for P dot. All right, so 4 state variables, the speed and position of each mass. Let me see. Okay, we'll come to that later. So let's start by writing the differential equations of motion here. Let's start with mass 1. I'm going to skip the free body diagram because I think at this point this is trivial. I would hope that this is trivial, and I already made a mistake on my trivial equation. P minus Q minus B1 P dot minus Q dot equals to M1 P double dot. That's the equation for the first mass. Does that one make sense? Sum of all forces equals to M1 P double dot. Force is going to the right, so that's positive. The damper and the spring K1 and B1 apply a force resisting motion that goes to the left, hence the negative sign. Are we good here? Yeah. What is the equation for mass 2? as the equation for mass 2. Well, now this damper and the spring are applying force to mass 2, but they are making the mass move towards the positive direction, so they are positive forces now. And we have K2 times Q, that's a force due to that spring, K2, and minus B2 Q dot, that's the force due to the damper B2, and that's equal to M2 Q double dot. Yeah, okay. All right, so here we have the two equations. Let me copy them. And let's move on. So let me just write them down here. There we are. Now let's move to the next step, define the state variables. We established that we need 4 of them, position and speed of each mass. So let's call x1 P, that's position of mass 1, and let's call x2 Q, position of mass M2. Let's call x3 P dot and x4 Q dot. This is random. We can choose another way to arrange them, but that's what I have here. Now, can we relate x1 and x3? What is the relation between x1 and x3? If x1 is P and x3 is P dot, then x3 equals to x1 dot. Very good. And x4, if x2 is Q and x4 is Q dot, then x4 equals to x2 dot. Very good. Aha, we solved already 2 of our equations. We have an equation for x1 dot as a function of other states. That's the first, that x1 dot equals to x3. And we also solved for x2 dot because that's equals to x4. We have 2 equations left, and these 2 equations that are left are gonna to come from the equations we just wrote, we just derived. But to do that, we need to rewrite our equations using this representation. So let's do that for the first mass. First mass equation is there. Sorry, I forgot this one, the double dot got lost in the copy and paste there. Let's use the first equation to rewrite that as a function of our states. U of t is the input. We'll leave as it is. It's the input minus q is k, excuse me, is constant. P and q are variables, state variables. P is x1 and q is x2. So we can simply write x1 minus x2. x1 minus x2 minus b1 times p dot minus q dot. So for p dot, what do we do? For p dot, we have 2 options. We have the option of going with x3, or we have the option of going with x1 dot. Which one should we choose? x3, exactly. Always the lowest derivative. So you have the option between first derivative and no derivative. Let's go with no derivative. So p dot becomes x3. And now you get it for q dot, we go with x4. And this is equal to m1 times what? M1 times p double dot. And what is p double dot? x3 dot. Exactly, x3 dot. We could have written x1 double dot, but remember that defeats the purpose because we are now using a second order equation. So always the highest derivative. So m1 times p double dot, which is the same as x3 dot. All right, so if x3 equals to p dot, take the derivative of x3, that's p double dot. Aha. That's another equation we are looking for. Now look at this equation here. We have only one derivative, and that's the derivative of state 3. And everything else is the input and other states. That's perfectly exactly what we were looking for. Let's move on to the other mass. It's down there, and let's rewrite that equation using the state. So P is x1, Q is x2, plus B1 P dot, we just did this, is x3, minus Q dot, which is x4, minus K2. Q is x2. This is really easy to make a mistake here. Minus B2 Q dot. What is Q dot? That's x4 equals to M2 times Q double dot. If x4 is Q dot, then x4 dot is Q double dot. So this is x4 dot. Nice. Now we have the fourth equation. That's the derivative of the fourth state. And it's only functions of other states. See, there's no other derivative in there, and everything else is either states or inputs. We are missing one equation here, which is the output equation. We chose the output to be P of t. So what is y of t as a function of the states? That is simply x1. And we chose, again, the output y to be the position of mass m1. So y of t is p, which is the same as x1. Any questions here? No? Yeah. Sorry, I can't hear you. We define the output to be p, right? So it could have asked you this: find the transfer function between p and u. So p is automatically the output. All right, so here we are just writing that in differently. We say if the output, if you want to know p, that's the output. So y, the output is p. We have to write that as a function of our states, and that turns out to be x1. But again, I could have chosen anything else. I could have chosen the output to be the force in the spring, for example. And that would be P minus Q divided by K times K. Right? It's completely up to us. Okay, so here are the equations we just derived. I just rearranged them, divide everything by 1 over m. So I have simply rearranged what we just saw, and you see that here I'm explicitly solving for the derivative of each state. Once again, all these equations have the derivative of each state, so one per equation, and that's a function of all other states and nothing else, and the input, of course. So now we can write our first equation in the matrix form. That's the state equation. X of t is a vector that has x1, x2, x3, and x4. So x dot is x1 dot, x2 dot, x3 dot, and x4 dot. And we have it here equals to a times x plus b times u. So let's start with this term, a times x. What goes in a? Let's look at x1 dot. What goes in matrix A for x1 dot? Now remember that A here is going to be multiplied by x1, x2, x3, x4. And if you want to reproduce the first equation, what coefficients do we need in the first row? Notice that x1 dot is only a function of x3. It's multiplied by 1. It's not a function of x1. It's not a function of x2. It's multiplied by 1 to get x3 and 0 for x4. All right, so I see some faces there. So what we are doing again is this equation here. We're reproducing that equation in the matrix form. So you have x dot equals to a times x plus b times u. Let's focus on the a times x. If you want the first equation, remember that you're multiplying this by that, this, that, and then adding everything up. All we need is x1 dot to be equal to x3. So it only takes one element there. Everything else is 0. And it's not a function of u. So we can assume we can put a 0 in the first row for vector, first cell for vector b. Tell me what x2 dot looks like. X2 dot is the second row in A, and what goes in there? 0, 0, 0, 1. Very good. 0, 0, 0, 1. Why? Because it's only a function of x4 and nothing else. So for B, it's also 0. Okay. Make some room here. Now let's look at x3 dot. So x3 dot is at a whole equation. And x3 dot, now we have things that multiply x1, x2, x3, and x4. What multiplies x1? That is minus k1 over m1. So focusing on this one. x2, we have k1 over m1. x3 minus b1 m1. And x4 b1 over m1. And we see u of t showing there, and u of t is multiplied by 1 over m1. Any questions about that one? Does that one make sense? Yeah? So what is x4 dot? Let's do x4 dot. What goes in the last row? Well, coefficients of all x's. That's k1 over m2 minus k1 plus k2 over m2 plus b1 over m2 and minus b1 plus b2 over m2. And there is no u, so that's 0. I just realized here you might have there could be a mistake in your solutions where that is written double dot in your copy. It's just a dot. Right? That's a typo. If that's the case, it's just a dot. I fixed it in my copy last night, but I think I forgot to upload. So those that are home, you can see B. So I'm gonna write B here because my image is in front of it. Is 1 over m1 0. Okay. Now notice that if we go to the equation in the center there, x dot equals to ax plus bu, and you multiply everything, we go back to the 4 equations we had. And now you can clearly see what influences what in the system. We can see the parameters that will influence the rate of change in the states. That's the big matrix A. And you also see where exactly the input affects the states. That's matrix B. And then through B, A is affected, and the system evolves that way. So that's one of our equations. The other one is the output equation. And for the output equation, we chose the output to be P of t, the position of mass 1, and that's equals to x1. So now we have to write this equation as shown here. So y of t is the output, and you want the output to be a vector c times x plus d another vector times the input u of t. The only equation we have is this one that gives us the output. So what goes in C, 1, 0, 0, 0. And in D, we have simply zeros. And if we multiply this out, we just go back to our original equation. But this tells us the output equation. Okay, we may end up with an entire expression for the output, depending on how we choose it to be, and then we represent that as a variable as well. Questions, comments, observations? See, really the tricky part here is to find the right set of states. And once that's done, then everything else should fall in place easily. Any questions? No? Okay, so if there are no questions, we'll move on. Now, one thing that I mentioned in the beginning is that the advantage of this is that we can solve for these equations using a matrix format. Well, that's that, and there's nothing much to say about it. But the other advantage of this representation is that we can put that in a simulation diagram. And this simulation diagram now will explicitly show us where these states are. And then you can probe them with the appropriate scopes in Simulink, for example, and get access to that variable directly. Let's do that. Let's take these equations that we just derived for the mass spring damper system. Here they are, a set of 4 equations. And let's draw a block diagram, a simulation diagram using this equation, and see how that looks like and how that compares with the other type of simulation diagrams we did before. So I started here, and yeah, let's do that. So we have here 4 equations. We can treat these equations as now any equations. We know how to deal with go from equations to block diagrams. 4 equations here. Where do we start? Remember from the previous lecture, where do we start when you have a simulation diagram? Start from the input. As the input shows up in equation, in the third equation for x3 dot. That's u of t. And here I accidentally called it u of s, but let me revert it to u of t. U of t. So let's start with equation 3. I'm going to do a trick here. We see that every variable is divided by m1. So let me multiply both sides of the equation by m1 for now, just to get rid of that. And then we just do 1 gain 1 over m1 for all of them together once we do the sum. Let's start with that big line for matrix 3. And we are starting from the left, sorry, from the right. We are creating on the right side of the equation that entire sum. So we're starting with u of t. That's the first element. To u of t, we have to add b1 times x4. Now we have the second element. We'll find x4 somewhere later. What else we need? You need to add negative b1 times x3. So b1 times x3. This is this term. So that's negative. Let's put a negative sign over there. What else? We need to do k1 times x2. That's that term. And then you have another term. I'm going to find some room for it here. That term is k1 times x1. And it goes in here, is negative, and then everything sums like that. So if you do, what we did here is the right side of the equation. What is the result of that? What is the result of this entire sum? What is it? X3 dot times M1, right? Because we will multiply everything by M1. So the result of the equation is the left side of the equation, basically, which is, why is that not showing? Oh, this wasn't showing. I was drawing here and it wasn't showing. So I'll give you some time to catch up there. All right, so when you do the entire right side of the equation, we have the left side of the equation, that's M1 times X3 dot. So it's here, M1 X3 dot. Multiply that by 1 over M1. What do we get? X3 dot. And what do we do with X3 dot? Now we can integrate that to get X3. So let's move it up here. Take the integral, and the integral is X3. Integral is X3. Interestingly, we have an expression for X3. X3 equals to X1 dot. So I can integrate this again to get X1. Does that make sense? Okay. If that makes sense, should we move to X4 dot? The equation for X4 dot? So if you go for the equation for X4 dot, we can start by adding everything up. Again, so one. Let me start with, okay, yeah. So let's do equation for X4 dot. Now let me just find the best logistics here. So that's X4, okay. All right, what do we have there? So let's just start with the first term. We need to find somewhere X4. And X4 is multiplied by negative B1 plus B2. Again, multiplying both sides here by M2 for now, so we don't need to worry about it. That is going to be added to X3 times B1, that's this term. We are going to add another term here, which is minus K1 plus K2. If you don't want to do this, let's be consistent and neglect that sign. So K1 plus K2, then you put a negative sign here. B1 plus B2, and you put a negative sign there, just to be consistent with the other notation. And then this times X2. And then we have K1 times X1. And you're adding everybody together here. What is the result of that operation? Each of this sum, each of this thing is one element in X4 dot. That's the right side of the equation. That equals to the left side of the equation. That is M2 X4 dot. So let's multiply this by 1 over M2 to get rid of that M2. And here we have X4 dot. Integrating X4 dot, we get X4. But what is X4? Well, X4 is simply X2 dot, going from this equation here. When we integrate this once again, we have X2. Yeah. Questions there? Now we can connect everybody. Let's connect all the x4s. So these are x4s. These are also x3s, x2s, and x1s. There we go. And now we can close the loops here. Where do we get x4? Oh, x4, this is going to be quite messy. x4 comes down here. x3, we can find x3 over there. x2 is right around the corner there. And what is the last one I didn't connect? x1. Where is x1? All the way up here. Well, all this for what? Well, for what? We can see now that each state is clearly identifiable in the diagram. Each state is clearly visible in our simulation. Here's one of them. That's one position. Here's a speed. Here's another position. Here is another speed. Behind them, we have the acceleration of each mass. Using the tools we had before, well, we had a nice simulation diagram, but the sum of the variables of interest were not as explicitly visible as we see them here. Where is the output of our system? The output was chosen to be x1 before position of one of the masses, so that's where the output is. But despite that one output, we also have access to everything else in the system. All other states are clearly visible in the simulation, and that's one of the biggest advantages of this type of analysis compared to the analysis we did before. Are there any questions? Now we can implement this in Simulink if you want. And simulate it that way. You can also use MATLAB with the equations, and there are tools you'll see in the labs, tools to solve for these differential equations using the matrix of linear algebra. There are 3 more exercises here. Of course, we won't have time to do all of them. We have 10 minutes left, so let's try to squeeze in one more. Are there any questions here before we move on? Everybody is really quiet, so if I don't hear any questions, I will just keep going. But if you have questions, always ask them, because if there's a question here, and later down the road, you're not going to understand what I'm talking about. All right, so if there's any holes in my explanation, just ask me, and I will gladly go through that now, and then later when it's too late, and then we have to go back and explain some concepts, which is fine too. But I'm just saying, I'm here to explain this thing. So if anything is not clear, it's my fault. Just ask me. I'll repeat this as many times as it takes. Okay, hearing no questions, let's do one more. Now let's do the opposite. Let's do the opposite. And I like this exercise because it's kind of a mix between simulation diagram simplification and the state space. So now we're going to go the other way. We have this system, this simulation diagram, and we want to find the state equations for it. These are the equations there. So what can we do here? Well, first we need to identify where the states are. And if you notice in our previous simulation, the states were right after integrators, because remember how we built it. We had differential equations, first order differential equations, that eventually we had to integrate to get the states. So where do we look for states here? Well, after the integrators. So there are 2 of them, 2 integrators, 2 states, one after each integrator. Remember once again, the equations were first order equations. They had to be integrated to give the states. So if you want to find where the states are, just look where the integrators are, and past the integrators, that's where they should be. Where is the output of our system? Where is the output of our system? That's y of s. Y of s. That's the output. And you have two states here, two integrators. I'm calling the first state x1 just after the first integrator, and x2 is the other just after in the second integrator. So let's do the equation. Well, let's look at this a bit closer here. If this is x1, then here we have x1 dot. And here we have x2 dot. I'm doing a mathematical crime here by mixing up time and Laplace with s and t. Don't do that. Yeah, I'll just do it here, but you get the idea, or x1s and x2s, right? That's the derivative of the states. Now, that's the equations we are looking for. Remember what we are looking when deriving the equations? These equations, first order equations for each of the derivative of each state. So we need equations for x1 dot and x2 dot as a function of all other states. So if we look at x1 dot, what can we write? What is the equation for x1 dot? X1 dot is u of t minus what? Minus x2 times k. x2 times k. State derivative, input, state. Good, that's the format we want. All right, so the signal here is, if the signal here is x2, then we are injecting here x2 times k. Does that one make sense? Sort of? I mean, basically finding an equation for the signal right here. Let's do the equation for x2 dot, and x2 dot is there. What is the signal at x2 dot? What do you have as a function of all other states? So if you're dealing with functions of other states, we can take it from here. We can take the signal here, and we can take the signal there. So it's a combination of three signals there. It's a combination of these three loops. So the first one is easy, is x1 times a. That's this signal injecting. That's x1 times a. Yeah. The other signal is the signal coming from the top here, which is plus x1 dot times f. x1 dot times f. And the third signal is this signal here, which is minus, well, there's a minus sign there, x2 times d. x2 times d. Does this second equation make sense? Yeah. There's something that is not quite ready yet in this equation. What is the problem with it? x1 dot, right? x1 dot shouldn't be there. We want an equation for x1 dot. That's the first one. We want an equation for x2 dot, but that is only functions of states. It cannot be function of derivative of states. What do we do there? Well, we can replace the first equation in the second equation, and then rewrite it as x2 dot equals to x1a plus u minus k x2k times f minus x2d. And this we can rearrange as x1 dot equals to x1a plus what? Plus minus kf minus d times x2 plus u of t times f. So these are the equations. Equation for x2 dot. Equation for x1 dot. What is the output equation? Output is y of t. And y of t is simply as a function of other states. What can you write for y of t? Any ideas? What would be a good candidate function for y of t? bx2, very good. B times x2. And here we have the output equation. All right, so now we can proceed to final step here. We have x1 dot, x2 dot. This is equal to matrix A times x1, x2 plus matrix B times the input, and the input is u of t. Sorry, this should have been, it doesn't matter. Put it this way, u of t. So what goes in matrix A? All coefficients of x1. For x1 dot, we have 0 minus k. And for u, we have 1. For x2 dot, we have, for x1, we have a. For x2, we have minus kf minus d. And for u, we have f. And for our output equation, the output equation is y of t equals to something times the states plus something else times the input. So for the states, we have y of t equals to x2 only. So you have 0 and b, that's coming from here. And the u of t is simply 0, 0. And this is the inverse process from the model to the state equations. Where is the key here? The key is to find where the state variables are. But we know that they are right after the integrators, because we started from a first order differential equation. We had to integrate them to get solution. That's where we can find them.